Hello everyone, my name is Martina-An, and as you say, I'm from NTNU, Norwegian University of Science and Technology in Trondheim, and I'm here today to present my work about the development of an interoperability approach for solar cadastre at high latitude. In fact, solar energy represents one of the most developed among the renewable energy sources and applied in the cities, and for this reason it becomes really important to study and evaluate the contribution of the solar potential into the built environment, because cities represent a relevant concentration for energy consumption. And it is really important also to study and evaluate the contribution of solar energy to the energy budget of buildings, neighborhoods, and also cities. Because this information can help a lot both the private users and also the stakeholders to make more informed decisions about some energy efficiency intervention at multiple scale. At high latitude, the PV panel installation has been increased a lot, especially during the last few years, and especially during the last one after the pandemic period. And assessing the solar potential also of the facades is very relevant for high latitude countries due to the low solar zenith angles reached for most of the year, and for the presence of the snow in the roofs for several months during the winter period. In this way, advanced and innovative technology for the renewable energy sources evaluation are represented by interactive urban energy planning platforms that can help the implementation of the design strategies within the existing urban environment, and specifically for the Specifically for the urban solar energy planning, we have some tools called Solar Cadaster, and this tool can facilitate users to make some preliminary decision about the PV panel installation into the existing built environment, and they can also calculate for example, some cost or benefits intervention, and also visualize the most available, the most suitable parts of the rooftops or also of the facade for the PV panel installation. In this regard, the novel contribution of this work is about the development of an interoperability approach for a preliminary version of a solar cadastre for the municipality of Trondheim, which was chosen as a high latitude case study. And this solar cadastre is in a preliminary stage for the moment, just for the roofs. And also in this work, I will present with this work the identification of the most usable and suitable rooftop areas in 3 different neighborhoods that I will show you later for the solar system installation. And also, one of the objectives of this study is the creation of a methodology that can support not just the private users, but also in the decision-making phase, the public authorities to develop some energy planning interventions. First of all, as I said before, we selected 3 different neighborhoods in Trondheim, corresponding to 3 different levels of density, starting from low, medium, and high density neighborhoods. And these are with different functional and morphological characteristics. For this study, the meteorological input data were collected using the Meteornorm software, while the geometrical input data corresponds to 3 different typology of files. The first one we used was the DSM file, which is the digital surface model for the shadow casting calculation, and also for calculating the slope and the aspect. The second one is represented by the building shape file, containing the 2D representation of the building footprints are enriched with the information about the building's function. And the last one was the CTGML file corresponding to the 3D building model of the 3 different neighborhoods, constructed with an automated reconstruction techniques. All these input were used for the creation of the solar model. This solar model is based on algorithm encoded in Java, and this was useful for the calculation of the yearly solar irradiation of the neighborhoods. These data, these outputs from the solar model were then post-processed with a Python script for the identification of the most available, the most suitable areas for the PV panel installation in the roofs. This area corresponded to the optimal part of the roofs corresponding to the solar irradiation, but also to the area without any impediments, without any object that can obstruct the PV panel installation. Okay. Here we can see the results about the estimated yearly solar irradiation for the 3 different neighborhoods. The first one, the A, is the low-density neighborhood. Here we can see that mostly of the surfaces are very high irradiated, and this is due for the morphology of the buildings, because the houses are small and they are far from each other, and the streets are very wide, so this can allow for a very high solar accessibility. In the neighborhood B, in the medium density neighborhoods, the areas of the roofs with a high solar irradiation are fewer, and they are limited to the south exposed roof slopes, while in the last one, the neighborhood C, the high density neighborhoods, the areas of the roofs with a very high solar irradiation are fewer, and this is due to the shadow effect of the surrounding buildings. After that, the annual solar irradiation maps were post-processed to identify the most suitable area which are available for the PV panel installation. First of all, we define the range value to consider the solar irradiation high and very high for high latitude countries, and we started from the literature to get this information, and for considering a portion with a high solar irradiation, we selected the raster pixel with a solar irradiation higher than 616, and we proceed in the same way to classify the very high solar irradiation portion of the roofs, considering a threshold value of 818. Additionally, the raster pixel representing the elements that can obstruct the installation of the PV panels were filtered out. These elements can be considered, for example, the roofs, the windows in the roofs, the chimneys, or for example, the ventilation or mechanical bodies. And we also filter out an inner buffer of 0.5 meters, as the solar panels cannot be installed in the proximity of the building's boundary. And we excluded from the analysis also the areas smaller than 5 meters square, as they were considered too small for the installation of a solar panel. The limited number of neighborhood case study doesn't permit to articulate some robust correlation analysis between the neighborhood density and the available areas in the roofs for the solar panel installation. But however, it is worth to highlight that the lowest value of the available surfaces are always associated to the high density neighborhood, and this is due principally to two reasons. And the first one, as I said before, is the proximity of the buildings that facilitate the shadowing with the surrounding buildings. And the second one is the lower ratio of the roof area and the total building volumes, because Having many apartments and many floors in the same building result in a greater presence of elements installed on a roof compared to a low or a medium density neighborhood with, for example, just one floor. That means, for example, one house, one flat. And another point is also that the fragmented interoperability approach that we developed need to be simplified for the large number of software and tools that were used. And here are summarized the main limitation of this study because, as I said before the just 3 neighborhood case study can limit the capability of identifying strong correlation between the model outputs and the neighborhood density, but also the weather data, because the weather data were collected by a meteorological station, which is located in the airport, that is 35 kilometers outside of Trondheim municipality. And in this case, we decided to use Meteonorm just to create a general and replicable workflow. Instead of using a local weather station, but relying on local data would allow to have more accurate results. And finally, as I mentioned before, developing the process by implementing multiple software and tools can bring to more accurate results, but using different working environment and different programming languages can also make the process to be more fragmented and not automated. Because, for example, in the file recognition steps, we need to fill manually all the, from when we switched from a software to another, all the information about the position of the files and yeah, just that informations. And about the future development in this field, may concern, for example, the enhancement of the workflow through the reduction of the fragmentation to reduce the computational time, especially extending the calculation for the whole city territory. After that, also increasing the number of the neighborhoods case study can help to find more robust correlation between the morphology and the solar irradiation. Exploiting the use of the local data and validating the results against the real measurement to find if we have some relevant results. Extending also the analysis to the facade by including the optimal properties of materials and the detection of the external and architectural elements in the calculation. And finally, the last point, which is one of the most important one for our project, because at the moment there are no solar web platform providing the extension of the usable area in Norway. Among the future development, there is the ambition to transform the 3D geometrical model joined with the solar irradiation calculation to create an interactive 3D cityscape platform for the that can be useful not just for the private users, but also for the municipalities and for urban planners to make to develop urban planning guideline and also to provide some recommendation to optimize the use of the solar energy, especially for the high latitude countries. Thank you.